talk about some research inside the BlockSec. So how we systematically to locating the flaws of blockchain or virtual machines. So this is work, team efforts of the researchers from BlockSec. Oops. Okay, so a little information about myself. So I got my PhD in 2015, and then I joined the Zhejiang University as a professor in 2018. I published papers because I'm a professor in Zhejiang University, and I'm also hack and build systems with real impacts. I like, I hack systems, but I also like building the secure systems. And a little information about BlockSec. So BlockSec was a security company founded in 2021, and we have a couple of tools and services which are freely available in the community, and most of the security researchers are using our Phalcon exploiter, to debug the transactions, to analyze the root cause of the exploits, and we also have MetaDock, MetaSleuth for the community. If you guys are the users of our products and have some suggestions, comments, issues, feel free, to contact me. So what's the motivation of this work, of this research? That's because blockchain has, play a very important role in today's decentralized world, and the virtual machine, the execution engine of the smart contract is virtually important. That's because if you execute a smart contract, the correctness of the execution of the smart contract is should be guaranteed by the virtual machines. And we have a lot of different blockchains, different virtual machines nowadays, and according to the DeFi number, we have more than 200 different blockchains with virtual machines with the capability to execute smart contract nowadays. So let me put some information of the Ethereum virtual machine. Ethereum virtual machine is the execution engine for the Ethereum network, and it is a stack-based virtual machine. It has some volatile memory, the stack, and the persistent memory for the account storage. So if we execute some instructions inside the Ethereum virtual machine, all the operands will be pushed on the stack. Like this one, we have push opcode. It will push the 2 value on the stack, and we then execute the push 1. It will also push another operand on the stack. After that, we have the S-store. S-store will fetch operands from the stack and then write all the memory inside the persistent storage, the account storage. During this process, the gas, it will consume the gas, which will be deduced from the sender's account, right? So if we have some bugs inside the virtual machine, inside the Ethereum virtual machine, it will cause serious consequence, right? It may, it will, cause the incorrect result of the smart contract execution, which will be, make the blockchain fork or some DDoS attack to the whole Ethereum network. And actually, it happens like the CVE 2021 39137. This is the bug inside the pre-compiled data copy smart contract inside the EVM. So basically, the data copy pre-compiled smart contract is to copy the data from the input buffer to the output buffer. So it works perfectly if we, the input buffer and the output buffer does not overlap. But if the attacker, they can trick the EVM to execute some instructions, and this instruction has the overlapped input buffer and output buffer. It will correct the buffer during the copy, right? So it will cause an incorrect execution result of the smart contract execution. So, and this happened in 2 years ago. And besides this publicly available bugs or vulnerabilities, so actually there are some bugs which has been fixed before they are exploited in the EVM. So because of the serious consequence, we need to have a system to detect this VM bug systematically. But it's not easy for a couple of different reasons. First, the EVM implementation is complicated. It's not easy for auditors to manually audit all these source codes. Second, we have different kinds of the Ethereum virtual machines. They are developers using the different languages, like they are using Rust, JavaScript, Go, and Python, and even Python, right? So the auditors, they need to spend lots of efforts, to start all these EVM virtual machines. Third, the different blockchains, they may have some customized features inside these virtual machines. So in order to solve these challenges, we use differential testing, to find the bugs inside the virtual machine implementations. So the basic idea of the differential testing is that if we have different implementations of the virtual machines, all of them comply to the same standard, right? So if we can feed the inputs to these virtual machines, if we feed the same inputs to these virtual machines, they should generate the same output, right? So we can observe the outputs. If we find that there are some difference inside the outputs giving the same inputs, then we should find some inconsistency between these virtual machines, and we can manually, analyze the implementation of these virtual machines to identify the root cause of these bugs. This is the basic idea. So how can we do that? First, we need to generate test cases which are feed into these virtual machines. In our system, we have the one test case consists of two different types of data. The first type of data is the transaction metadata, right? The transaction metadata means we need to feed the transactions with the same from address, same to address, same balance, same nonce to the virtual machine. Another test case is the pre-state. The pre-state means the current snapshotted state of the whole blockchain, right? So even if we have the same transaction, but if the pre-state is different, then we will not get the same output. And after talking about what the test case are, the next problem is how to generate a test case, right? So in our system, we take two different ways to generate test cases. One of the test case, one strategy is that we reuse the historical transactions. That's because blockchain, all the transactions inside the blockchain are public, and we can rerun these historical transactions, right? We can feed all these historical transactions and the pre-states to different virtual machines and observe their outputs to observe their post-transaction states. So the second strategy is that the historical transactions is very good, but most of them are the normal transactions, right? Most of them consist of the normal contract, smart contract code. But because we are doing the security testing of a virtual machine, we want to generate some, bytecode which are not common. We want to generate some transactions which are not observed in the historical transactions. So another strategy is that our system can generate the transactions and the smart contract code from scratch, and we then mutate all these transactions and the smart contract code and feed it into the virtual machines. So this is the typical strategy used inside the fuzzing techniques. I'm not going to go deeper into this because it's well known in the community. After that, we need to compare the outputs to find any inconsistency inside the virtual machine implementations. So inside our system, we observe both the persistent states, that is account storage, and the volatile states like the memory and the stake. So the persistent state is easy to observe, right? We can read all the storage after executing a transaction, and we can compare nonce, compare all the storage values after executing a transaction. For the volatile state, we periodically compare the memory values, the stack values, the program counter, and all the volatile states during the execution, right? One thing need to mention that we need to, we cannot compare the volatile state instruction by instruction because it will consume much of the computation. It will make the fuzzing process very slow. After that, we need to eliminate the false positives. That's because if we observe the inconsistency into the different virtual machine implementations, that does not necessarily mean there is a bug inside of the virtual machine implementation. That's because some virtual machines, they have their own customized features, like they have their different way to calculating the gas, right? So we have observed some inconsistency in some virtual machines, but they are normal. They will not cause any inconsistency into the final persistent state. That should be fine. Okay. So to evaluate the effectiveness of our system, and we have developed a system inside the BlockSec, and we have applied this system to a couple of different virtual machines, like Aurora virtual machine, which is a L2 virtual machine on the top of the near blockchain, and the Moonbeam, the EVM OS, the FEVM from the Phalcon, and the Polygon ZK EVM, the ZK implementation of the Polygon network. It turns out that our system are very effective. We only run our system on these implementations for a couple of weeks, and we found, it's because it's a continuous efforts, and for each virtual machine we run on our system like a couple of weeks, and we successfully found 14 bugs. Some of them have been fixed by the, most of them have been fixed by the vendors, and some are still in the discussion with them. As an last, I will use a case study, to illustrate why the root cause of the bug and how our system covers this bug. So this is a bug we detect in the Aurora engine. So in the Aurora engine, there is a mod exp contract. It's a pre-compiled contract, right? So the computation of this pre-compiled contract is the module exponential calculation. So basically, we needed to calculate the gas consumption of this pre-compiled smart contract. And in the if we implemented it correctly, so basically it will calculate the iteration used for calculating this the iteration count used to calculating during the calculation, and then we will calculate the gas cost using the last line of the code. We need to multiply the complexity and iteration count. But the Aurora engine, they started to change one line of the code, right? They changed the one line of code from the maximum iteration count N1 to just iteration count. So what's the problem here? So if the iteration count, the number of the iteration count will be 0, so it will make an incorrect calculation of the gas, because the multiplication complexity multiply iteration count will be 0 in this case, right? So it will make the gas consumption calculated very smaller than expected than the correct value. So this is the bug we identified. So how we identify this? Because we feed the same transactions to the Aurora engine and the vanilla gas client, and we observe some difference, right, inside the gas during the differential fuzzing process. And then we manually analyze why there is a difference, and we reported this bug to the Aurora engine. Okay. So the takeaway of this research of my talk is that the blockchain virtual machines are not as robust as you may expect, right? Because they are code developed by the developers, and the developers are humans, and humans make humans do wrong things, right? Humans, they will make errors. So we cannot expect the virtual machine implementation as robust as we expect. And to detect this vulnerability inside the blockchain virtual machines, we have developed a system that leverages the differential testing techniques to find all these bugs. And currently, our system is running inside BlockSec, and we also have a system that can privately deploy, to different virtual machine, to the different L1 or L2 blockchains. So if you are interested, free to contact us. Thanks. That's all for my talk.